Okay, so today we're going to go ahead and start a new section. We're going to start 5.2 verifying trig identities. So this is super similar to what we've already done. It's just adding a little bit extra. So first thing I want to talk about is the difference between a conditional versus an identity. So a conditional statement might be something like this. Sine of x is equal to 0. So if I think about my unit circle, sine of x is equal to 0 here. And it's equal to 0 here. It's equal to 0 at pi over 2. And it's equal to 0 at 3 pi over 2. So we can see that this is only true. It's only true for select values. Now, that right there is what's called a conditional statement. An identity statement is something like this. It's something that's always true. So for example, sine squared x plus cosine squared x is equal to 1. This is what's called an identity. So an identity is something that's always true no matter what I plug into it. So just want to make that distinction there, and then we're going to keep on moving. Okay, we're actually going to come back to this at the end. It says guidelines for verifying trig identities. We're going to come back to that at the end. First, we're just going to practice using fundamental identities. So what I want to do, this is called verifying. I want to verify that secant squared theta minus 1 all over secant squared theta is equal to sine squared theta. Now, there are so many ways to do this. Literally, I couldn't list them all day, but there are so many ways to do this. So I'm going to do it the way that I would think to do it. But if you happen to want to use a different method, you are more than welcome to do so. So let's go ahead and see how this works. Usually whenever I see like a fraction and there's just a binomial in the denominator and there's a polynomial in the numerator, sometimes it's a good idea to kind of distribute out the denominator. So what I mean by that is I can rewrite it as this. Secant squared theta minus all over secant squared theta minus 1 over secant squared theta. So do you see here, if they both have a denominator secant squared theta, I can actually split them up into something like this. Okay, well, secant squared theta divided by secant squared theta is 1, and so this is going to be 1. And let's think about my reciprocal identities for a minute. Reciprocal identity tells me that 1 over secant is cosine. So 1 over secant squared has got to be cosine squared. Okay, all right. This is kind of looking a little bit better. So really what we're trying to do is we're not trying to move anything from one side to the other. So when we're verifying, do not move sine squared to the other side. Don't move anything to the other side. Just keep moving on one side. So I chose to simplify the left side, so I'm going to continue to simplify. Does this equal sine squared? Well, if I think for a minute about the Pythagorean identity, so the Pythagorean identity says that sine squared theta plus cosine squared theta has got to equal 1. Well, if I subtract cosine squared theta on both sides, I get that sine squared theta is equal to 1 minus cosine squared theta. So is this true? Yeah, I just proved it, and this is what's called verifying. So I give you one thing, and you work just on one side of the equation to prove that it's equal to the other side. Okay, we're going to go ahead and start the second one. Now, here's another hint that I would use when I'm verifying. Pick the side that looks the most complicated to simplify. So pick the side that's the most complicated to simplify. The reason you'd want to do that is if I said that cosine squared plus sine squared equals 1, if I pick 1 to be the side I simplify, 1's already kind of simplified. There's not a lot to work with there. So pick the side that you have more to work with. I'm going to pick the side that's more complicated. So I want to know, does 2 secant of theta, does it equal, I'm putting a question mark, I don't know, does it equal this whole thing? Well, I have two fractions. I want to probably combine them. In order to combine them, I'm going to have to get a common denominator. So what I'm going to multiply by is I'm going to multiply this by the denominator of that and this by the denominator of that, if that makes sense. So I'm going to multiply this first one by 1 plus sine theta all over 1 plus sine theta. And I'm going to multiply this one by 1 minus sine theta all over 1 minus sine theta. And the reason I'm doing this, I'm trying to get the same denominator. So what I end up with is 1 plus sine of theta all over 1 plus sine theta times 1 minus sine theta. So hopefully this is ringing a bell. It's really similar to a question we did in class. And then we'll say minus, not minus, it was plus 1 minus sine theta divided by 1 minus sine theta times 1 plus sine of theta. Hopefully we can fit that on there. Well, we see that I have a common denominator, so I'm going to go ahead and combine these because I have a common denominator. So let's see, is this equal to, if I combine these, I'm going to get 1 plus sine of theta plus 1 minus sine of theta, so I'm just combining the top, all over a common denominator of 1 plus sine theta times 1 minus sine of theta. So I want to know, okay, does it equal 2 secant of theta? Well, getting my highlighter out for a minute, I'm going to see there's a positive sine theta here and a negative sine theta here. That means that these are going to cancel. So really what I'm left with is 1, 2. I'm going to get 2 in the numerator, and I'm going to have 1 plus sine theta in the denominator. So 1 minus sine theta. If I go ahead and distribute this out, I'm going to get 2 all over. Let's use FOIL method. 1 minus sine theta plus sine theta minus sine theta squared. Well, if I use my highlighter again, I'm going to see that the sine thetas are going to cancel, the middle ones. The sine thetas are going to cancel. And so what I'm left with here, if I look at this, I'm left with this. 2 all over 1 minus sine squared theta. Okay, going back to my Pythagorean identities. 1 minus sine squared theta, let's go ahead and take this Pythagorean identity and see what that would be. If I moved sine squared theta over instead, so instead I move sine squared theta over, so minus sine squared theta minus sine squared theta, I would get that cosine squared theta is equal to 1 minus sine squared theta. So I know that this whole denominator right here is cosine squared theta. Okay, so let's go ahead and rewrite that one more time. So what I get is 2 divided by cosine squared theta. Well, isn't 1 over cosine theta, isn't that secant? So 2 over cosine squared theta has got to be 2 secant squared theta. Well, I just proved it. These two things are the same. If I simplify this original expression, I get regular 2 secant squared theta. Okay, let's just try a couple more examples. All right, so the next example, does 2 cosecant squared theta equal 1 all over 1 minus cosine theta plus 1 plus cosine theta? So for this question here, it's really, really similar to the last one. So I'm actually going to ask you to pause the video for a minute, and I want you to try this one on your own. So I'm just going to pause the video for a minute. Okay, so hopefully you paused the video and you tried this one on your own. So what you should have gotten is it's the same process. Get the same denominator by multiplying each by the denominator of the other. And what we're going to get is 2 over 1 minus cosine squared theta. Well, that's the same as 2 over sine squared theta, which is the same thing as 2 cosecant squared theta. All right, let's just try one more. All right, the last one here, tangent squared theta plus 1 times cosine squared theta minus 1 is equal to negative tangent squared. So this question here is asking, okay, I got to pick the side that's more complicated. Well, the side that looks more complicated is this side, so I'm going to go ahead and use the FOIL method. I'm going to go ahead and expand this out by distribution. So tangent squared theta times cosine squared theta, so we're going to get tangent squared theta, I keep saying theta, sorry, times cosine squared x, minus tangent squared x plus cosine squared x minus 1. And the question is, does it equal negative tangent squared? Okay, well, let's go ahead and try to simplify this. So right now, I'm not seeing particularly anything too much yet, but let's try and simplify this. So what I could write everything in terms of sines and cosines. That's a decent strategy. So I'm going to go ahead and do that. I'm going to rewrite tangent squared x as sine squared x all over cosine squared x. times cosine squared x minus, I guess we could write this again as sine squared x all over cosine squared x plus cosine squared x minus 1. Okay, well, if I see this here, okay, sine squared x over cosine squared x times cosine squared, these cosines are going to cancel. So what I'm left with is sine squared x minus sine squared x over cosine squared x plus cosine squared x minus 1. Get my highlighter out for a minute. We have a, oh, we don't want that. Okay, all right, minus 1, sorry. Minus 1. Okay, so I'm going to get my highlighter out for a moment. Notice here I have cosine squared x and sine squared x. They're both positive, so using the commutative property, I could put them together. Sine squared x plus cosine squared x using the Pythagorean identity is 1. I'm going to rewrite that as 1. That's the same thing. All right, minus, in fact, I'm actually going to just write this as tangent because we're getting close to the answer. This is the same thing as tangent, minus 1. The question is, does that equal negative tangent squared x? So at this point, we're really, really close to the answer. Notice how these two 1s are going to cancel. And so I get negative tangent squared x is equal to negative tangent squared x. Okay, so there are a couple of key takeaways that I want to go over with you guys. So there are a couple of guidelines, and I actually have them written in the book. But basically, a couple of the guidelines would be this. So first guideline, I'll type it. So our first guideline is just try. Is it not going to let me type? Oh. Okay. Oh, I guess I can't type. All right. So basically, you just need to work on one side. So the first thing is work on one side, preferably the more complicated side. So that's your first thing that you need to do when you're verifying a trig function is to work on one side, preferably work on the side that looks more complicated because you're going to have more options to deal with. All right, so next thing you want to do is look to factor. So look to factor, that's going to be a big tell for you. In addition to that, you could also look to add fractions. You could look to squaring a binomial, which we haven't done quite yet, binomial. And you could also look to, I think that's all the ones on that one. All right, let's go on to the next one. And these are just from the book. Obviously, you can come up with your own strategies. I have my own, but this is the one from the book. You could look for an opportunity to use fundamental identities. So really, if you're thinking about what we've used thus far, you could think about reciprocal. You could think about the Pythagorean. And you could think about quotient. I think those are the only ones that you know at this point. Quotient. Okay, so that's one thing that you could do. Next one, number 4 of things that you could do. Basically, this is kind of what I did in the last problem, is if all else fails, convert everything in terms of sine and cosine. So that's what I did in the last problem there. So signs of sines and cosines. It's kind of like a last-ditch effort. I do it all the time, even when I don't have to, because in general, if you convert everything in terms of sine and cosine, you're usually going to come up with a solution. It might not be the fastest way, but it is a way. Lastly, this is in the book, always try something. If you could just always try something, maybe you're not going to be right, and that's okay. The thing about 5-2 is that you're really not always going to be right on these. And it's kind of hard to teach this because there are so many ways to be right. There's also so many ways to be wrong. So just always try something, and eventually you're going to get the hang of it. So that's really all that I have for you guys today. If you have any questions, make sure you leave a comment, and I will be back with you on Thursday to discuss.